So, going back to the beginning of the year, we talked about the intermediate value theorem, where I gave you that magic trick that no one was really impressed by. I had you all graph things, and I then didn't look at any graphs and said, I can promise you that somewhere your graph has a y value of 4 or a y value of 2. And you said, well, of course that has to happen because we've got our lowest y, our highest y. It's got to equal all the y values between them. Intermediate value theorem was used to guarantee that a specific y value would occur on the graph. We have this other theorem, though, called the mean value theorem that guarantees something about the slope on our graph. So here's what I would like you to do. I would like you, in each of these graphs, to draw in a secant line that passes through the two endpoints. So in number 1, I want a line that goes through that point and that point, which means it's going to look something like that. Make sense? Do this for 2, 3, and 4. Hopefully you have some secant lines like mine. That should not have been super difficult. This mean value theorem says that under a couple different requirements that I'll give you in a little bit, somewhere on our graph, the slope of the tangent line will equal the slope of that secant line. So here's what's going on. In number 1, we found the slope of our secant line to be, well, the slope of the line that you see over here. I think there's a place on the graph where the tangent line has the same slope. I'm thinking maybe about like here, because if I graph a tangent line over there, looks like it has about the same slope. I'm going to label that as C. At that particular x value, which I just labeled as C, the slope of my tangent is the same as the slope of that secant line through the endpoints. Couldn't have said it was over here because my slope would look something like this. Couldn't have said over here because my slope would have looked something like that. But at the point where I drew in the tangent line, do you agree that the slopes kind of agree? Mean value theorem guarantees, again under a couple requirements, that the slope of the secant line has to equal the slope of some tangent line somewhere. I would like to see if you can figure out a place, or maybe there's more than one place, on 2, 3, and 4, where the slope of the tangent line equals the slope of the line through the endpoints. And again, there might be a few places in some of these graphs. This should work in all 3 of the problems. These all meet the requirements I haven't given you yet. But this slope thing will work in all 3 of them. raising your hand, how many places did it work in number 2? Who has an answer? How many places did you find where the slope of the tangent equal the slope of the secant? Is that a hand, Nathan?
Yeah.
How many places? Yeah, I would agree with that. Maybe like one about here or something, because I think the slope of the tangent line will look something kind of like that. And maybe the other about over here. Not at the minimum, but kind of close to the minimum, because I think the slope of the tangent line will look something like that. So I'm going to label them C1, C2. 2 places. Did you see that there were 2 places there? I think 3 should be pretty easy. Where is this going to happen in number 3? Quasi? At the maximum, because the slope we're trying to guarantee that occurs is what? What's the slope of that secant line? 0. And where is the slope 0? Well, at a maximum or a minimum. So right over there. How many places did you get for number 4? Matthew? 2. So, like about here maybe? I think that'll work. Tangent line looks like that. And then maybe about here? Tangent line looks kind of like that. So we'll call that C1, and we'll call this one C2. You know what? I do think there is another one. Yeah, like kind of about over here, maybe. But what this mean value theorem says is, again, under certain requirements, we're guaranteed that there's at least one place where the slope of a tangent line, the derivative, will equal the slope of the line through those endpoints. Why do we care about this? Not yet. We'll get into that a little bit later today. But first I want to kind of give you the theorem and show you how to work with this stuff. But did the ideas from the graphs make a little bit of sense to you? Notes up, please. And we are going to take a look at section 3.2. It is November 13th. Section 3.2, the mean value theorem. And here's what our theorem says. Again, this is called the mean value theorem. If f of x is, there are 2 requirements on these functions. The graphs I gave you, anything you noticed about those particular functions? They're continuous. First of all, if f of x is continuous on some closed interval between a and b, we'll see why that's important a little bit later. There is something else, though, you should have noticed about the graphs. Maybe something that they didn't have. I didn't see any sharp turns. I didn't see any vertical tangents. And differentiable. If the function's continuous on a closed interval from a to b, and differentiable on, actually it doesn't have to be, excuse me, doesn't have to be differentiable at the endpoint, so I'm just going to say the open interval, a comma b. Then there exists a c value such that f prime of c, which equals the slope of some tangent line, equals, well, the slope of our secant line. And we'll get a formula for that in just a moment. I have some function. Here's the slope of my secant line. And looks like the place where the tangent line is the same thing as that is right about there. That's my C value. The slope of the secant line. Well, I'm just going to use my normal y2 minus y1 over x2 minus x1 formula to find that. I think my y values are f of b and f of a. I think my x values are just b and a. That's the formula for the slope of my secant line. By the way, the slope of the secant line, there's a special name for it. It's also sometimes called the mean value. We have a function that's continuous on a closed interval and differentiable on an open interval. Slope of the line through the endpoints, slope of that secant line, must equal the slope of some tangent line somewhere. And as soon as a few people finish copying, I'll show you how we're going to use this. So for our first example, we are going to determine if the mean value theorem can be applied to the function I'm about to give you. If so, we are going to find the slope that is guaranteed and then find the value of c such that f prime of c equals f of b minus f of a over b minus a. We are going to apply our mean value theorem to the function f of x equals 3x squared plus 6x minus 5, and we're going to do this on the closed interval from -2 to 1. Don't do anything yet. Just copy down the plot. And I'm not going to bother writing these directions for every other problem. This is exactly what we're going to do for all the problems we look at today. We'll figure out, can we even apply the mean value theorem? And there are a couple things I'm going to need to explicitly see in your work. Then, if we can, we'll go and figure out the slope that's guaranteed and where the function will take on that slope. First, we need to explicitly check the two requirements. Is this function continuous? Sure, all polynomials are continuous. I need to actually explicitly say that, though. Number one, f of x is continuous on that closed interval that we care about, on the interval between -2 and 1. Is it differentiable? Well, let's find the derivative and make sure the derivative is continuous. F prime of x, so this is an easy derivative, just 6x plus 6. Therefore, f of x is differentiable. On the open interval between -2 and 1. So this mean value theorem applies. So here's what we're going to do. We're going to go and we're going to calculate the slope of the secant line. We're going to do the problem f of 1 minus f of -2 over 1 minus -2. Well, go do that. Find f of 1 without a calculator. Find f of -2 without a calculator. Plug into the original function. Subtract those answers. Do the division. See what you can do. Let's get that slope. can you get a slope of 3? The mean value theorem guarantees that somewhere the slope of the tangent line will equal 3. That's the slope we were trying to guarantee. Now I want to figure out where exactly that happens. Where is the slope 3? How can I go about doing that? How can I calculate where the slope is going to be 3? One person has an idea. Anyone else have an idea? Sabrina. So I plug it in for x? Yeah, set your first derivative equal to that slope. We know the slope. We know the derivative gives us the slope. We are just going to set f prime of x equal to 3, and we're going to solve. Well, I already calculated f prime of x when I tried to prove that the thing was differentiable. So I'm going to say 6x plus 6 equals 3. 6x equals negative 3. Looks like this is going to happen at x equals 1/2. When x, no it doesn't. When x is negative 1/2, the slope should be 3. Let me see if I can show you what's going on here. I'm not sure if this will continue.